I was not happy with the lack of eloquence to my explanation today of L'Hopital's rule, so I'm going to try it again. The first version of L'Hopital's rule you'll see is a one-shot L'Hopital's rule. It's kind of like a one-step one where it says if f and g are differentiable, so you need to actually be able to find derivatives of f and g. F is over g. And f of a equals g of a equals 0. They both equal 0 right here. And g of a does not equal 0. Then you can just do it once and you get this new ratio. So for example, if you wanted the limit as x goes to 0 of sine x over x, which you can't just evaluate by plugging in 0, you can apply L'Hopital's rule here because both the top sine of 0 is 0 and x equals 0 when you plug in 0. And the derivative, when you take the derivative of this, you get 1, not 0. So you can apply L'Hopital's rule, and the arrow with the h, that means you've applied L'Hopital's rule, is going to be equal to, what's the derivative of sine? Cosine at 0 over 1, which is, in this case, just 1. So this is the first iteration. This is one shot. You've applied L'Hopital's rule once. But you can generalize L'Hopital's because you can apply it multiple times. And here's the more general form. So f and g both have to be differentiable, and f of a and g of a both have to be 0. What it says is the limit of the left equals the limit of the right, which is just the derivative separately of the numerator and the denominator, provided the limit on the right exists. So it means this is true as long as you can actually find this limit. And what this definition allows for is repeated application of L'Hopital's rule. So you can apply L'Hopital's rule, and you know that this is equal to the limit as t goes to 0 of the derivative of the top, which is going to be e to the t minus 1 over the derivative of the bottom. Well, how can you find this? Well, this definition allows for repeated application until you can actually find this. So all you have to have is the top 0? Is the bottom going to 0? Yes. So we're working with the indeterminate form, 0 over 0. So you can apply L'Hopital's rule again and end up with the limit as t goes to 0 of e to the t over 2. And in this case, you can plug in 0 directly and you end up with 0. So the more general form allows for repeated application of L'Hopital's rule because you only need f of a and g of a to be 0. And then you can start taking the limit, repeatedly applying L'Hopital's rule. And what we mentioned briefly at the end of class was that there was a second indeterminate form. So you do have the indeterminate form 0 over 0 as expressed right there, but then you also have an indeterminate form where the limit as x goes to a of f of x and g of x go to plus or minus infinity. So you have plus or minus infinity over plus or minus infinity, one or the other. It's fine. So 0 over 0 or infinity over infinity. Note, this is not 0 over infinity, which is directly solvable, or infinity over 0, which is a different problem entirely. So you have infinity over 0 over 0, an example of which would be the limit as x goes to infinity. And notice that as x goes to infinity on this, this blows up and becomes huge. And as x goes to infinity, this also becomes huge because this right here ends up going to 0. But this right here goes to infinity. So you do have an indeterminate form here of infinity over infinity. In this case, it's going to be positive infinity over positive infinity. So if you apply L'Hopital's rule in this case, like this, you end up with 5 minus e to the x, negative e to the x. 5 minus e to the negative x all over 7. And again, this is the limit as x goes to infinity. In this case, if you wanted to write all of this out, you have the limit as x goes to infinity of 5 minus limit as x goes to infinity of e to the negative x over the limit. And again, this is not something you would generally write out, of 7, which is just going to be 7. But this right here, it's important to realize this is going to 0. And the other two are going to 5 and 7. So this would go to 5 over 7. So again, we have two indeterminate forms, infinity over infinity or 0 over 0, and you can repeatedly take the derivative until you end up with a constant in the denominator or something whose limit is a constant.